Hi and Assalamualaikum students. This is tutorial 04 and in this video I'm going to cover tutorial for chapter 2.2. Question number 1. Air flows steadily in a pipe at 300 kilopascal, 77 degrees C and 25 meter per second at a rate of 18 kilogram per minute. Determine the diameter of the pipe. In this question, you have air that will be flow steadily through a pipe. The pressure of the air is 300 kilopascal, temperature is 77 degrees C. The velocity here is 25 meter per second and the mass flow rate here is 18 kilogram per minute. So we need to find the diameter of the pipe. So basically the diameter we can find from equation area. So the area of a pipe is equal to pi r square or pi d over 2 to the power of 2. So from this equation we can find d. After we rearrange, we will get this equation in which we have to first find the area. So in order to find the area, we can find through this equation. A is equal to mass flow rate multiplied with specific volume over velocity. But from the question, we cannot find the specific volume, so we have to find. In order to find the specific volume, we can use the ideal gas equation, which is V is equal to RT over P. So we have to find one by one in order to find diameter. First, we find specific volume. We substitute all the values inside, then we will get this equation. R here is R for air, then we can get from table A1, temperature and also the pressure of the air through the pipe. So after we solve, we will get 0.3349 meter cube per kg. So from V, we can substitute into A equation. After we substitute, we will get this. So if you notice inside here, we have to change first minute to second. Because of the velocity here is per second, so we should change from minute to second. So after we solve, we will get the answer. The area is equal to 0.04018 meter square. Next, the value for A we substitute into this equation in order to get diameter. Then we will get the value for D is equal to 0.0715 meter. So this is the diameter of the pipe. Next, question number 2. Air enters a nozzle steadily at 2.21 kg per meter cube and 40 meter per second and leaves at 0.762 kg per meter cube and 180 meter per second. If the inlet area of the nozzle is 90 cm square, determine A, the mass flow rate in kilogram per second through the nozzle, and B, the exit area in centimeter square of the nozzle. In this question, we have a nozzle in which the air will enter this nozzle from velocity 40 meter per second increase to 180 meter per second, and also it is given in the inlet the density of the air, which is 2.21 kg per meter cube, and also the density of the air at the outlet of the nozzle, which is 0.762 kg per meter cube. So for A, we have to find the mass flow rate, in which the mass flow rate we can find from this equation. Rho 1, A1 and V1. This V is velocity. So we have all the values for rho, A and also V. So we just substitute in, we will get this. We have to ensure that the area is in meter. So we have to convert from centimeter to meter. After we substitute, we can solve, then we will get the mass flow rate is equal to 0.796 kg per second. So this is mass flow rate. Next, we have to find the area at the exit. So by using this equation, we can just rearrange and we will get, but we need to find the area of the exit. So rho 2 and also V2, we should use the rho at the exit and also velocity at the exit. So we have the rho and also the V, so we just substitute in. So M, we will use the M that we found in A, which is 0.796. We substitute in. Then we will get the value for A at exit is 0.0058 meter square. So this is how we find the A exit. Next, question number 3. Steam flows steadily through an adiabatic turbine The inlet condition of the steam are 10 megapascal, 450 degrees C and 80 meter per second, and the exit conditions are 10 kilopascal, 92% quality and 50 meter per second. The mass flow rate of the steam is 12 kg per second. Determine A, the change in kinetic energy in kilojoule per kg, B, the power output in megawatt, and C, the turbine inlet area in meter square. In this question, we have an adiabatic turbine in which the inlet of the steam is at pressure 10 megapascal, 450 degrees C and 80 meter per second. The outlet is 10 kilopascal, X is equal to 0.92 and also the velocity is 50 meter per second. A, we need to find the change in kinetic energy, and by using the equation for kinetic energy, we can find the change of kinetic energy. We will use this equation in which the velocity at state 2 to the power of 2 over 2 minus velocity at state 1 to the power of 2 over 2. Because we are given with the velocity at state 1 and also state 2, we can just substitute in, then we will get the answer. So after we solve, we will get negative 1950 meter square per second square. But we need to find the change of kinetic energy in kilojoule per kg. So we need to convert from meter square per second square to kilojoule per kg. So we need to multiply with this conversion. Then after we solve, we will get negative 1.95 kilojoule per kg. So this is the change in kinetic energy. Next B, we need to find the power output. So the power output means the W out. So we need to find the negative W out. By using first law of thermodynamics for open system, we can find the negative W out. So this is the first law of thermodynamics for open system. Please do not get confused. For closed system, in this equation, it is delta U. But for open system, it is delta H. Do not get confused, okay? Next, we neglect what is unnecessary, which is PE and also Q, because it is adiabatic. So KE we have to take into account because of we are provided with the velocity, and just now we calculate the change of kinetic energy, so we have to include the change of kinetic energy. So from here we can get negative W out is equal to M H2 minus H1 plus M negative 1.95. The change of kinetic energy we have found just now, so we can use it to substitute in here. So now we have to find the H2 and also the H1. So if we look at this diagram, we need to find first the phase for each state. State 1 and also state 2. For state 1, according to the pressure 10 megapascal and temperature 450 degrees C, we can find that T is higher than T saturated at 10 megapascal. So it means that at state 1, the phase is superheated. So in order to find the H1, we can find through table A6. So H1 is 3242.4 kJ per kg. Next, we have to find the H2. Before we can find the H2, we need to determine first the phase. So because of we are given with quality, so we know that the phase for state 2 is saturated mixture. So from table A5, we have to find the H1 by using this equation. By referring to pressure 10 kilopascal, we can find the HF and also HFG. The X is given, which is 0.92. So then after we substitute, we can get the value for H1, which is 2392.5 kJ per kg. Now we have found the H2 and also H1, so we can substitute inside this equation in order to find the W out. So then we substitute all the values, then we solve, we will get the W out is equal to 10.2 megawatt. So that's how we find the W out. Next, we have to find the turbine inlet area. So in order to find the area, we can find through this equation. In this equation, we need to have the specific volume and also the velocity. So the velocity is given, and now we have to find the specific volume. And because of at the inlet, the phase is superheated, so from table A6, we can find the specific volume at 10 megapascal and also 450 degrees C. So the specific volume, we will get 0.029782 meter cube per kg. After we substitute inside here, and also the velocity 80 meter per second we can substitute inside here, and after that we will get the answer 0.00447 meter square. So that's how we solve question number 3. Next, question number 4. Refrigerant 134A is to be cooled by water in a condenser. The refrigerant enters the condenser with a mass flow rate of 6 kg per minute at 1 megapascal and 70 degrees C and leaves at 35 degrees C in an isobaric manner. The cooling water enters at 300 kilopascal and 15 degrees C and leaves at 35 degrees C at constant pressure, neglecting any pressure drops, and determine A. the mass flow rate of the cooling water required, and B. the heat transfer rate from the refrigerant to water. From the question, we have a condenser in which we have two stream inlet, which is H2O and also refrigerant, and also two streams outlet, the outlet for refrigerant and also the outlet for H2O. So for each stream, it will be labeled with number, in which inlet for water is 1 and outlet is 2, inlet for refrigerant is 3, and the outlet for refrigerant is 4. So the water is at 15 degrees C and 300 kilopascal and leave at 25 degrees C at constant pressure, in which the outlet pressure is 300 kilopascal. For refrigerant, it will enter the condenser at 70 degrees C at 1 megapascal, and also the mass flow rate for refrigerant is 6 kg per minute. So it leaves the condenser at 35 degrees C in isobaric manner, so the pressure at outlet for refrigerant is 1 megapascal. So now we need to find the mass flow rate of the cooling water, or MW. Because of this device is condenser, so the KE, PE, Q and also W is not involved here. So from first law of thermodynamics for open system, we just consider the enthalpy for each stream. First, we gather the enthalpy for inlet and equal to the enthalpy at the outlet. We will do like this. We can see here, this is the stream for inlet and this is the stream for outlet. 1 and 3 is inlet, 2 and 4 is outlet. And we have to know that the mass for inlet and outlet, it has no difference. So we can represent the mass flow for stream 1 and also stream 2 as MW, and the mass flow rate for stream 3 and also stream 4 will be represented by the MR. Next, we rearrange this equation according to the mass flow rate. So this side is for water and this side is for refrigerant. So now we need to find the mass flow rate for water. So from here we have the mass flow rate for water, then we can rearrange into this. So in order to solve this equation, we need to find one by one the H1, the H2, H3 and also H4. The MR is given, just that all the enthalpies we have to find. At stream 1, we need to know first what is the phase at this stream. So after we have checked by using the temperature and also pressure, we have found that the T given here is lower than the T saturated. So means that it is compressed liquid. So from table A4, we can find the H1 is equal to HF at 15 degrees C, and it is equal to 62.982 kJ per kg. Next, at stream 2, after we have found that at stream 2 it is compressed liquid as well. So from table A4, H2 is equal to HF at 25 degrees C, and it is equal to 104.83 kJ per kg. Next, at stream 3, from 1 megapascal and 70 degrees C, it is found that the phase at stream 3 is superheated. So from table A13, by referring to 1 megapascal and 70 degrees C, we can find the H3 is equal to 303.85 kJ per kg. Next, at stream 4, we have found that by using 35 degrees C and 1 megapascal, the phase at this stream is compressed liquid. From table A11, we can find the H4 is equal to HF at 35 degrees C, and it is equal to 100.87 kJ per kg. So now we have found H1 until H4. Then we can substitute into this equation. we will get in this form. So after we solve, we will get 29.1 kilogram per minute, and this is mass flow rate for water. For question B, we need to find the heat transfer rate from the refrigerant to the water. So means that we need to find the Q that is coming out from the refrigerant into water. By considering at the water stream, the Q transferred from refrigerant is the Q in into the water stream. After we consider the energy balance at the water stream, so we will get Q in plus mH1 is equal to mH2. H1, Q in and H1 is the inlet into this stream, and the outlet from this stream is the enthalpy at 2. Because of we have found the H1 and also H2, so we can find the Q in. Before that, we rearrange this equation. Next, we just substitute the H2 and also H1 and also the MW that we have found in question A. So after we substitute, we will get the answer for Q in is equal to 1218 kilojoule per minute. So that is how we solve question number 4. Question number 5. Refrigerant 134A at 1 megapascal and 90 degrees C is to be cooled to 1 megapascal and 30 degrees C in a condenser by air. The air enters at 100 kilopascal and 27 degrees C with a volume flow rate of 600 meter cube per minute and leaves at 95 kilopascal and 60 degrees C. Determine the mass flow rate in kilogram per minute of the refrigerant. Hint, delta H for air is equal to Cp delta T and Cp is equal to 1.005 kilojoule per kg degree C. So in this question, we have a condenser in which we want to cool down the refrigerant by using air. Refrigerant enters the condenser at 1 megapascal and 90 degrees C and leave at 1 megapascal and 30 degrees C. The air enters the condenser at 100 kilopascal and 27 degrees C, and given here is the volumetric flow rate, which is 600 meter cube per minute, and the air leaves the condenser at 95 kilopascal and 60 degrees C. So as usual, for condenser, we just have to consider on the enthalpy. So we can rearrange the equation from the first law of thermodynamics for open system according to the inlet and also outlet. From the question, we need to find the mass flow rate for refrigerant. So we can rearrange the enthalpy for each stream into this equation. This is the inlet and this is the outlet. We have the mass flow rate for air and also mass flow rate for refrigerant. Next, we rearrange this equation according to the mass flow rate for air and also refrigerant. After we rearrange, we will get the MR is equal to MA in bracket H2 minus H1 over H3 minus H4. Now we have to find each enthalpy. But before that, the stream 1 and so stream 2 is air, and we cannot find the enthalpy for air from the property table. So this enthalpy change for air stream, we can change into Cp T2 minus T1. For H3 and also H4, it is refrigerant, and the enthalpy for stream 3 and also stream 4 we can find from property tables. So we just find the enthalpy. So now this equation, it can be like this. So now we have to find the H3 and also the H4. At point 3, when we consider at 1 megapascal and also 90 degrees C, we have found that the phase at this stream is superheated. So from table A13, we can find that the H3 is equal to 324.64 kilojoule per kg. For stream 4, after we check at 1 megapascal and 30 degrees C, we have found that the phase at this stream is compressed liquid. So according to table A11, H4 is equal to HF at 30 degrees C, and it is equal to 93.58 kilojoule per kg. So now we have already found the H3 and also H4. Then we can substitute into this equation, and we can substitute also the T2 and also T1 at air stream. But before we can solve this, we need to find first the M for air, because we are given with the volumetric flow rate. So M for A we can find through this equation, volumetric flow rate over specific volume, but the specific volume is not given, so we need to find first the specific volume. So for air, in order to find the specific volume, we can use the ideal gas equation, which is V1 is equal to RT1 over P1. R is the gas constant for air, T1 is 27 degrees C, and P1 is 100 kilopascal. After we substitute inside here, the V1 we will get 0.861 meter cube per kg. We take this value and substitute into this equation, so we will get the mass flow rate for air is equal to 696.9 kg per minute. So from this value, we can substitute inside here, then we can solve the mass flow rate for refrigerant. After we substitute, we will get this. And if you can see this, 1.005 is Cp, and Cp is given from the question. Then we can solve and we will get 100 kg per minute. So this is the mass flow rate for refrigerant. Next, question number 6. Refrigerant 134A enters an adiabatic compressor as saturated vapor at negative 24 degrees C and leaves at 0.8 megapascal and 60 degrees C. The mass flow rate of the refrigerant is 1.2 kg per second. Determine A. the power input to the compressor, and B. the volume flow rate of the refrigerant at the compressor inlet. In this question, we have a compressor in which this compressor needs the power input to operate. So the power input that we need to calculate is actually the W in. And you have to remember that the compressor, the direction of W should go into the compressor. And this is the adiabatic compressor, so Q is equal to 0. Refrigerant enters this compressor at 1.2 kg per second. Temperature is negative 24 degrees C, and the phase of the refrigerant enters this compressor is saturated vapor. The refrigerant leaves the compressor at pressure 0.8 megapascal and temperature 60 degrees C. So A, we need to find the power, in which the power is actually the W in. From the first law of thermodynamics for open system, we can find the W. But before that, we have to neglect the unnecessary. So from this equation, we can neglect Q, KE, and also PE. So now it can be simplified into W in is equal to delta H. It is equal to mass flow rate of refrigerant multiplied with H2 minus H1. Now, in order to get the W in, we have to find the H2 and also H1. First, we look at state 1 here. Because of the phase of this state is saturated vapor, so we just go to the table A11 and we can get the H1 is equal to Hg at negative 24 degrees C, and it is equal to 235.94 kJ per kg. For state 2, in order to find the H2, we have to find first the phase. After we have checked at pressure 0.8 megapascal and temperature 60 degrees C, we have found that T given here is higher than the T saturated at pressure 0.8 megapascal. So means that the phase at this state is equal to superheated vapor. So we go to table A13 and we can find the H2 in this table, which is 296.82 kJ per kg. So now we have already found the H2 and also H1, so we can substitute inside this equation in order to get the power input. So after we have substituted all the values inside, then we will get the answer is equal to 73.06 kJ per second. Next, we need to find the volume flow rate at the inlet, which is V1. In order to find the volume flow rate, we can use this equation, which is mass flow rate for R multiplied with the specific volume at state 1. This specific volume we can find from the table A11, in which at table A11, because of it is saturated vapor, so V1 is equal to Vg at negative 24 degrees C, and it is equal to 0.17395 meter cube per kg. So we substitute inside here like this, then we will get the answer 0.209 meter cube per second. So this is how we solve question number 6. Question number 7. Refrigerant 134A at 800 kilopascal and 25 degrees C is throttled to a temperature of negative 20 degrees C. Determine the pressure in kilopascal and the internal energy in kilojoule per kg of the refrigerant at the final state. In this question, we have a throttling valve in which this throttling valve will throttle refrigerant at pressure 0.8 megapascal and temperature 25 degrees C into temperature negative 20 degrees C. Then we need to find the pressure and also the internal energy at the outlet. So in order to find the pressure and also internal energy, we should determine first what is the phase at the outlet from this throttling valve. But in order to find the phase, we need at least 2 info. But given in the question is only 1 info, so we need another info. So we look, this is throttling valve, and one principle that we need to know about throttling valve, it is isenthalpic. The enthalpy at the inlet is equal to enthalpy at the outlet. So means that we can have another info which is H2 in order to find the phase for this state. But before that, we have to find first what is the enthalpy at the inlet. Because you are given with pressure and also temperature, so it is easy for us to find what is the H. But before that, we need to find first what is the state at the inlet. According to pressure and also temperature, after we have checked, temperature at state 1 is lower than the temperature saturated at pressure 0.8 megapascal. And because of that, the phase for state 1 is compressed liquid. Because of it is compressed liquid, we can find at table A11, and H1 is equal to HF at 25 degrees C, and it is equal to 86.41 kilojoule per kg. So means that the H2 is also 86.41 kilojoule per kg. So now we have 2 info, which is enthalpy and also temperature. So we can determine what is the phase for state 2. From table A11, we check the enthalpy at temperature negative 20 degrees C, and it has found that H2 is between HF and also Hg. And because of that, the phase for this state is saturated mixture. So because of it is saturated mixture, so P2 here is equal to P saturated, which is 132 kilopascal. Next, we have to find the U2. This is saturated mixture, so U2 we can find through this equation, UF plus X UFG. But before we can find the U2, we have to find first the quality. So we look here, we have enthalpy, and the quality we can find through enthalpy through this equation. X is equal to H2 minus HF over HFG. By referring at table A11 at temperature negative 20 degrees C, so we can find the HF and also HFG. So after we substitute into this equation, we will get the X is equal to 0.2861, and now we can substitute this value inside this equation in order to find the U2. So now we can find the U2 from this equation. UF and also UFG we can find from table A11 at T negative 20 degrees C. So we substitute all the value inside here, then we will get the U2 is equal to 80.74 kilojoule per kg. So that is how we find the internal energy for throttling valve. So we have finished our chapter 2.2. I hope you understand, and if you have any question, you can directly ask me. Till we meet again in the next video, thank you and Assalamualaikum.